Hello everyone. So last section, we have learned a few several ways of writing system of linear equations. But in this section, we are going to analyze the solution sets themselves. A linear system is homogeneous or homogeneous if that can be written as the form as ax equals to 0. So here, well, again, A is m by n matrix. And the thing on the right hand side is a 0 vector in Rn. So note that, so there's always an obvious solution. So if you multiply whatever by 0, then you actually get a 0. So the homogeneous system always has 0 solution. And we call this as the trivial solution. Okay? Okay, then the question is, when does the homogeneous system have a non-trivial solution? Or that is to say, are there any like non-zero x such that a times x becomes 0? Or if you write that in augmented matrix, then it is equivalent to ask whether the matrix given by A and 0 have non-trivial solution. So if you think about the problem in terms of the augmented matrix, then when you RREF the given augmented matrix, like suppose that you have pivot position for each rows, like every variables are basic variable, then the answer is always specified or the solution is unique by 0 because we have a trivial solution. So the condition to have non-trivial solution is to have at least one or more free variables. And here, mathematicians frequently abbreviate if and only if as IFF. So whenever you see IFF, then that means if and only if. In this exercise, we're going to see whether the given homogeneous system has a non-trivial solution. So the plan is, first, REF the given augmented matrix, and then find the pivot position, and see if the system has any free variable. So basically, the augmented matrix for this system of equation is given by 1, -3, 7, and 0, -2, 1, and -4, and 0, 1, 2, and 9, and 0. And we first want to eliminate the first column. So we add 2 times R1 into R2, and we subtract R1 from R3. Then the given augmented matrix is row equivalent to 1, -3, 7, 0, 0, -5, 10, and 0, 0, 5, and 2, and 0. Now, to make it upper triangle matrix, we add R2 into R3 and multiply by -1/5 by R2. Then the given matrix is row equivalent to 1, -3, 7, and 0, 0, and 1, -2, 0, 0, 0, 12, and 0. So we have pivot positions for each variables. And this tells us that there is no free variables, which means there is no non-trivial solution for the given homogeneous system. Does it make sense? So part B is very similar problem to the previous problem. So let's pause the video and try out the part B of this exercise. Okay, so the augmented matrix for this system of equation is given by, I guess, it's 1, 3, -5, and 0, 1, 4, -8, and 0, -3, -7, 9, and 0. So we need to reduce this to row echelon form to see whether there is a free variable. So the row echelon form will be appeared in a second. Okay, so from here, we can tell that x3 is a free variable, and x2 equals to 3 times x3, and x1 equals to -4 times x3. So this tells us that the solution vector x that consists of x1, x2, and x3 can be written as negative 4x3, 3x3, and just x3. And we can certainly factor out by x3, which gives you x3 times negative 4, 3, and 1. So we call this as a parametric vector equation, and it is parametrized by x3. So what I mean is the answer is parametric vector equation if and only if the solution is a multiplication of a variable and a constant vector. And in this problem, our v is just negative 4, 3, and 1. So here, the things that you want to note is that we found all solution of ax equals to b is a multiple of v, or in other words, all multiples of v is our solution. And if you draw the solution set, then the solution set is the line that passes through the origin. So if you draw the solution set to xyz coordinate, then the vector v is somewhere around here, and the solution set should look like in this way. We can also describe solutions to non-homogeneous system in parametric vector form as well. So here, non-homogeneous means that ax is not equal to 0, but equals to some non-zero vector b. So for example, a is something like this, and b is a vector which is not equal to 0. And the way we solve the problem is very similar. So again, you RREF the augmented matrix, and then see if there are any pivot positions. And lastly, identify all free variables. So here, note that A, the given matrix, is the same as the previous example. So you can follow the same row reduction to get the row echelon form of the given augmented matrix. And RREF of this matrix will appear in a second. Oops, I realized that the matrix is actually from part B. So here we can see that x3 is free variable, and x2 equals to 3x3 minus 4, and x1 equals to negative 4, x3 plus 16. So if you write the solutions in parametric vector form, then we have the vector x equals to x1, x2, and x3. And x1 was negative 4 x3 plus 16, and x2 equals to 3 x3 minus 4, and x3 is just x3 because this is a free variable. So if you separate the answer into two parts, then we can write this as negative 4 x3, 3 x3, and x3 plus 16, negative 4, and 0. Or in other words, the solution equals to x3 times negative 4, 3, 0, plus 16, negative 4, and 0. And note that how similar is this term compared to the previous exercise, which is over here. So for non-homogeneous system, like ax equals to b, where b is not equal to 0, then the solution looks like x equals to p plus tv. So here we have p over here, and t is x3, and v is this vector. And for the homogeneous system, where b is actually 0, then we just get x equals to tv. And the point is, these two only differ by the vector p. Okay, so geometrically, so if you draw the solution set into a coordinate plane, so let's say you have a vector v over here, and p is something looks like in this way. And we know that the solution set to the homogeneous equation is a line passing through the origin. So the equation of this line is x equals to t times a vector v. And if you add p to the solution set of the homogeneous equation, then we get a line translated but parallel to the original one. So this is the graph of a set of vectors x equals to p plus tv, where p is one particular solution of the non-homogeneous equation, and the solution set to ax equals to b is a line parallel to the line passing through the origin. So the theorem below summarizes what we have learned for this section. So suppose that we have consistent non-homogeneous matrix equation and P to be a particular solution. Then the solution set for the non-homogeneous equation is of the form W equals to P plus TV H, where V of H is any solution to the homogeneous system. So intuitively, we can think of the solution set of AX equals to B is simply a solution set of AX equals to 0 that is translated by any particular solution P of the non-homogeneous equation.